Welcome back. Up until this point, we've been talking about electric forces. But today, we're going to start talking about another construct, which is called the electric field. And I think you're going to be happy after this discussion, because so far, when we've been talking about electric forces, we've needed a lot of information in order to calculate the problem. And I think when we study electric fields, we might get a better physical idea for what's happening to the universe when we add charges to it. But first, I think we need to make sure that we understand the terminology involved. I'm going to use the word field a lot in this class. For example, the title of the course is Fields in Spacetime. So what is a field after all? Well, a field is a function, and that's really all it is. It's a function that maps every point in space to some value or set of values. That is, a field is some characteristic of space and time, such that I can return some value given every single point in space and at every time. When the universe has a field, that field exists everywhere. Sometimes the value of that field might be 0, but that doesn't mean that the field doesn't exist. And all of what we're studying in electromagnetism and special relativity deals with studying how these fields and the value of those fields evolve as I wander through space and time. So when you think about a field, you want to say, well, if a field exists, the thing we're going to be talking about today is the electric field, my goal is to find out, well, what is the value of that field at every point in space at all times? Now, when I say value, I could be talking about a single number. For example, we know about fields that return a single number. We usually call these scalar fields. For example, the potential energy, or the gravitational potential U, which is just equal to minus G, right? This is a field. Now, it's a pretty trivial field because the gravitational potential in this room is a constant everywhere. Right? I could also write down the gravitational potential in terms of Newton's universal law of gravitation, where it's minus G times the mass that I'm studying divided by R. And this thing is also a field, but now it varies depending on how far away I am from the mass. Force is also a field. Now, if you've watched a lot of science fiction, you've heard people talk about the force fields, right? Well, that's actually a real thing. Because if I have a force that's defined everywhere, for example, the gravitational force, minus mgc hat, this is a field that returns a vector at every point in space. And therefore, the force is a field, and it makes it the force field. So if I try to think about this in terms of electricity and magnetism, I'm really going back to this problem that we talked about in calculating electric forces. At the heart of this problem is the following logic. I have some set of charges in the universe, right? So on the left-hand side, I have a couple of point charges. I have a charge distribution rho. I have a bunch of charges that exist somewhere in the universe. But I also have a test charge. And by test charge, I really mean, what is the thing I'm studying? What is the object that I care about? All of the questions that I'm being asked, are they questions about what is that object doing? Right? There's always one object in the study. It's the one that we draw our free body diagram for. And so my problem is always, what do all of the charges in the universe do to influence this test charge that I have? And so far we've used the electric force to draw that conclusion, but in order to draw that conclusion, I needed to know, apropos, or in the beginning, what that test charge was. Since the logic goes, everything in the universe, all of these other charges, is actually doing something to the universe, I wonder if I can create a mathematical construct that represents what is the influence of all of the charges in the universe, and can I account for that before I actually do a calculation and find out what the force is on a test charge. perhaps another way of saying that is, if I remove the value of the charge that I'm studying, so that at any point later in the future I can replace that charge with some other charge, can I mathematically describe what happens to the universe just because there are charges involved? Well, of course I can. And the thing that describes that is the electric field, which we call E with a vector symbol over it. Now, if I want to then back up and I want to define this in terms of the mathematical constructs I already have, I actually can do this pretty intuitively. So let's take our expression for the electric force due to some unknown charge distribution, right? And now you'll see I've already started talking about this in terms of the way we want to frame the question, right? F naught has always been what is the force on Q naught given any other arbitrary charge distribution. And so I already have this Q naught that's somehow separate. I also have this vector R, which translates to R hat, which points from my charges in the universe to the point that I'm studying. So most of the stuff inside the integral doesn't care about Q naught at all. In fact, on the right-hand side of this expression, the only time Q naught ever appears is as a single constant. And it's not even stuck inside the integral. Now we tend to not deal with this in terms of the integral form, and so what I'm first going to do before I do the mathematics here is take my integral form for the electric force, and I'm going to write it in differential form, which is I take the derivative of both sides, and I get a little contribution to the force is equal to 1 over 4 pi epsilon naught Q naught, the test charge in question, times dq over r squared times r hat. If I want to get rid of the Q naught, that is, if I want to define a structure that doesn't know anything about Q naught, well, the obvious thing to do is to take this df naught and divide it by that charge, right? So I'm going to take my little what contributes to the force, and I'm going to divide it by Q naught, and that thing is going to be what I'm going to call dE. Because everything else in that expression contributes to the understanding of what's happening to the universe at the point that I'm talking about if I know where all of the charge distributions in the universe are. And this also means that if I calculate what the electric field is, and I want to get back the electric force, all I need to do is multiply that electric field by the value of the charge that I'm interested in. And that's actually something that's really cool. So all of the mathematics that I've been doing to describe the electric force could equally have been done to describe the electric field, and then at the end of the problem I just have to multiply by the test charge that I'm looking at, and I get out what the electric force is. And so dE, which is the electric field, is given by 1 over 4 pi epsilon naught dq over r squared r hat. And this is a beautiful differential form that I can use for one-dimensional charge distributions, two-dimensional charge distributions, three-dimensional charge distributions, and then once I calculate the electric field, at some point, right, I need to study this at some point in order to calculate that vector r, but I can calculate the electric field at some point, at any point, at an arbitrary point, and then I can always just multiply that by whatever charge I want to put there, and I get out the electric force. Okay, let's do a couple of examples. First, the sort of most straightforward one. I just have some charge in the universe, a single charge, nothing else, no people, planets, or puppies, just a single electric charge Q, and I want to calculate what is the electric field due to this. Well, in studying this, I have not a 1 or 2 or 3-dimensional charge distribution, I have a 0-dimensional charge distribution, which means that my differential dq is just Q, right? And I'm gonna change my differential to just the charge because I can't break up a charge that exists at a single point, right? That's a 0-dimensional object. Which also means that I can't integrate over it, and so the differential electric field turns out to be just the electric field, right? It's just the I can if I'm only looking at a single point and I'm not doing an integral over all space, I'm just identifying a single point as my charge distribution, then my electric field is just going to be the differential for the electric field is going to be the total electric field. And therefore, I can write down the electric field due to this point charge is pi epsilon naught times q over r squared r hat, where of course r, this vector r, points from my charge distribution to whatever point in space I'm interested in. Now notice that the magnitude of the electric field doesn't depend on whatever direction I'm going in, right? The only thing that the right-hand side of this expression says is that if I were to take the magnitude of both sides, the magnitude of the unit vector is 1, that the magnitude of the electric field only depends on how far away you are squared. The direction, though, the direction of r hat then is always going to point in the direction of r, which of course always points away from q. And so my electric field, which I'm going to draw in blue here, is always going to be pointing away, or in the direction of r, it's always going to be pointing away from this charge q, if q is greater than 0. And so I've noticed something really interesting here. So when I look at this expression for q greater than 0, I always have an electric field that's pointing outward. It's getting weaker and weaker and weaker as I get further away. If I have a charge that's negative, I have an electric field that's pointing towards my charge that's getting weaker and weaker and weaker and weaker and weaker as I move away. But the electric field for a positive charge is always moving away from the positive charge. If I want to think about what effect that would have on another charge then, so now let me put in my q naught just as a thought experiment here. Well, if q is positive, the electric field is pointing away from q. If q naught is positive, then the force on q naught is going to be q naught times E. Well, that means that the force is going to be in the direction of the electric field, and the force is going to be away from q. And that's a simple thought check to make sure that I have all my signs right. If I have two positive charges, they're going to repel each other. If either of those signs had been different, if one of those two had been different, then either the q that goes into the electric field would have changed the sign, or the q naught that goes into the electric force would have changed the sign, and I would have had an attractive force. If both signs had been different, then those two minus signs would have canceled each other out, and I would have had a repulsive force again. A lot of people jump at this point to saying, you have to think about the electric field direction as the direction that a positive test charge would go, or the direction in which a positive test charge would be accelerated. And that boils down to this formula here. If I have an electric field that points in some direction with some magnitude, the force is going to be proportional to that. And if I put a positive charge there, that force is going to be in the direction of the electric field. As a much harder example, let's think about a charge distribution now that's two-dimensional. Okay, so I have an infinite sheet of charge in the xy plane, so it goes off to infinity in all directions. Now, my charge distribution dq is given by the charge density sigma times dA, which is sigma times dx times dy. So that plugs in dq in my formula here. If I need to calculate what r is, right now that's going to be hard because now I have to think about a vector that points from my charge distribution to the point in question. So if I take an arbitrary point in my charge distribution and I point it at the point in question, well, if the z component here, so p lies along the z-axis, right? If the z component is positive, then this vector is going to be pointing up, but it's always going to be pointing in the opposite direction of x and y. Let me say that in a better way. If I look at where I've drawn the charge, the infinitesimal piece of charge here, then I'm at a negative value of y and a negative value of x, but r points in the positive x direction and the positive y direction and the positive z direction. And so in order to calculate r from x, y, and z, I have to change the sign of x, I have to change the sign of y, but I keep the sign of z the same. This is the art that I was talking about in our last video, that when I define r, I have to be a little bit clever as to making sure all of these signs are right, because the r always points from the charge distribution, which is in the xy plane, to the point in question, which is along the z-axis. I can then do things like calculate the magnitude of r, which is the square root of x squared plus y squared plus z squared. And I can do things like calculate r hat, which is going to be minus x minus y z divided by the square root of x squared plus y squared plus z squared. And so I get, when I plug all of these things in, that dE, the differential contribution to the electric field, is 1 over 4 pi epsilon naught. I have to plug in dq, which is sigma dx dy, times r hat, which is minus x minus y z divided by r squared. Well, I'm going to combine that with the denominator of r hat, and I get x squared plus y squared plus z squared to the 3 halves. Okay. Now this thing, I can then integrate both sides, and my charge distribution goes from x equals minus infinity to infinity, and y equals minus infinity to infinity, and I can write down those two integrals, and I get this expression that actually calculates what the electric field is as a vector integral. But you have to pause here, because this expression, as nice as it was to write down, and don't get me wrong, most of the physics is done at this point. I now have to delve into calculus for quite a while before I get to the final answer. But most of the physics is done here, except I have a lot of integrals left to do. You might think I have 2 because there are 2 integral signs, but I actually have 6, because all of those integrals distribute into each of the components of the vector on the right-hand side. And therefore, I have 6 different integrals to do, which I can do, right? I can take that and I can distribute it through. When evaluating these integrals, I can play a couple of tricks. For example, I see that for the x component, I have x over something that's even in x, and therefore I'm multiplying an even function times an odd function over a symmetric domain, which gives me 0. Same thing is true for the y component. The z component is a messier integral. I've done it in 2 steps here, but at the end of the day, I end up with a pretty easy and pretty expression that says that the electric field is just in the z direction and is actually a constant. And so somehow this infinite sheet of charge, which had so many variables in it at the top of this page, reduces at the end of the day to an expression that says the electric field due to an infinite sheet of charge is constant, points in the z direction, under the assumption, I was assuming, of course, that the point that I was studying was above the xy plane, but I have a constant electric field that has the value given here. But before I end, I want us to really just take stock of what the electric field really means, right? I have now a structure that tells me what happens to the universe when there are charges in it. Sure, I might have to do messy integrals. Sure, I might have to worry about summing over point charges correctly. But really, whenever I have a positive charge, electric field lines are going to move away from it. Whenever I have a negative charge, electric field lines are going to move towards it. When I sum all of those together, I get the electric field of the universe. And when I evaluate that at some point, all I have to do is multiply it by a charge, and then I get a force. And I think that's really the beautiful part of studying the electric field.